Hubble constant with strong lensing to modeling of strong lensing to now transdimensional modeling of strong lensing, and I'm sure some substructure also pops up and micro lensing. So please take it away, Tansu.
Thank you, Simon. So, hi everyone. So I'm Tansu Daylan. I'm a new LSST Catalyst Fellow at Princeton University, and also I'll be joining the faculty at WashU following next year. So I will be talking about the work I've done a couple of years ago, which has implications for today's discussion. I hope you are not getting bored with the strong lensing stuff. Bear with me. What I will try to do is give you a thorough introduction of strong lensing, because I would lose half of the room if I did that. I will just highlight a couple of problems that I think are important in this problem, and then immediately jump into my main material, which is going to be probabilistic cataloging. Okay, so again, I'll probably just mention that this is the twin quasar discovered in 1979. And in fact, the whole idea was proposed by Einstein. Now we look at this JWST image and wow at it. And strong lensing can give us a lot of information. It can allow us to weigh galaxies and clusters. It can also allow us to infer the Hubble constant, or at least do our best in doing so, based on Schur's 1964 idea. And on top of that, it also allows us to do substructure. However, for LSST, this is less relevant because ground-based photometry can't really do substructure because this is typically millilensing. You've got really small subhalos. So I will not really spend a lot of time on this. The one problem we probably all know is the mass sheet degeneracy in strong lensing, that you can rescale your convergence and your source locations to pretty much get the same constraints. And you have to do dynamical data in addition to photometry to really get rid of that degeneracy. The other problem with using strong lensing to do cosmology is substructure. And this is not mentioned a lot because we tend to focus on methodology and getting the data. But whenever we look at a strong lens system, it's important to appreciate the amount of substructure there is in the mass model. And in order to really do science with substructure or strong lenses with substructure, we have to find a way to really marginalize out the bias that is introduced by substructure. And I think this is sometimes taken as an opportunity, sometimes as a challenge. It kind of depends on what you are trying to do with it. And finally, there's the interlopers. There's the lens along the line of sight. And there's been recently interesting work in this direction. And what I will be discussing next will apply to both substructure as well as the interlopers. So let's get into it. So this is just a summary of the three problems I mentioned. And I want to jump into so-called probabilistic cataloging. So let's take a step back. And I just want to introduce some very basic concept about stats. So in statistics, we are typically doing so-called inference. Given some quantity, we want to infer another quantity. And let's call these X and Y. Typically in statistics for science, we have some data. I'm referring to it as D here, and some model with n dimensions. And each of these models have some parameter vector. Its size is set by the model itself, the amount of complexity it has. And then there's generative inference, which is that you take a model and then you so-called forward model it to get the data. Now, these are the jargons I will be or have been or will be using. There's the forward modeling from the model into some M sub D, which then gets compared to the data D. And the two objects are connected by the so-called likelihood function, which is the probability of getting the data under the model with that specific dimensionality. Now, again, some more jargon, bear with me. It will be more clear why I'm talking about this. So the idea of cataloging, or the notion of cataloging, is the inference of a certain number of so-called elements. In astronomy, we are used to the idea of so-called cataloging the stars on the sky. So that means inferring their positions and fluxes and colors potentially. And I'll be referring these to these as elements, which is just an abstract way of referring to them. Now, confronted with such an inference problem, we like to think about non-Gaussian covariances, situations like this, when you have two parameters and they have some non-Gaussian covariance. So the worst thing you can do is fit for the best fit, and then take the curvature around it, which is the Hessian, and then just claim that that's your uncertainty. But obviously there's a big banana-shaped uncertainty here, which would not be taken into account if you did that. Now, typically, astronomers are great in realizing that and tackling that. But what about the same problem across dimensions? Typically, this is swept under the rug. We don't mention it. No one mentions it. No one thinks about it. So here is a thought experiment. Think about the cataloging problem. So this is a Fermi-Lat high energy data, but don't worry about that. Just treat that as a pixel of photons, and you've got some. Oops. Ooh. It's not playing. Okay. Nope, it's not working. Okay, I was going to illustrate the degeneracy here, but it's not working, so I'm going to wave my hands. So here, you could basically fit this image with one source, or two sources that are slightly separate, or three sources, or four sources, and you just don't have a good idea whether this is a single or multiple source. So there's a so-called transdimensional degeneracy in the problem. So how do you tackle that? Well, this is a schematic illustration of what's going on. Your likelihood is a function of models. Here, each point on the x-axis is a separate model, and each has a different dimensionality. So basically, sometimes the likelihood differences might be very small. And if you just go for the best fit model, you'll be missing out the fact that there are many other roughly equally likely solutions. And I'm not talking about a single parameter here. This is transdimensional. So there's, for example, just give numbers. There's a point source model with 5 sources, and there's a point source model with 3 sources, and they're roughly equally the same. So you cannot really go pick one model when you're trying to constrain some other dimension or some other parameter. Now, these might sound very abstract, but they actually directly relate to the previous couple of problems I've been talking about, especially the Hubble tension, the Hubble constant problem, which I will come back to at the very end. So I've already talked about the fact that we have these non-Gaussian covariances, and we're typically okay in treating them, but maximum likelihood cataloging or inference typically misses out on the transdimensional degeneracies. And in order to really start thinking about these transdimensional degeneracies, first you have to be Bayesian. So you have to really like this formula. And this is your posterior if you're a Bayesian. And then also on the way, introduce the hierarchical modeling, which was, by the way, discussed in the previous talk. So I will rely on that introduction and won't really talk about that in detail. But once you're so-called transdimensional, Bayesian, and hierarchical, you suddenly arrive at a statistical framework, which I put under the umbrella of probabilistic cataloging. So this was the subject of my PhD thesis a few years ago. It's implemented in Python, initially applied to gamma ray data, but the next paper on the right, the 2018 paper, is on strong lensing. So basically, a year after the initial code, I put in a strong lens likelihood function, which can then treat strong lenses transdimensionally. And the idea is really simple. So you've got some model M with the parameter vector theta and some other model with parameter vector theta prime. In usual MCMC, what happens is you have these. Oh, this is not playing either. Okay, thank you. Well, all right. So we'll have to live with whatever we have. So in MCMC, what you do is you just switch steps. So basically, you take proposals to walk in a fixed dimensional parameter space. But in so-called reversible jump Markov chain Monte Carlo or the probabilistic cataloging, there's an additional thing, which is you traverse dimensions. And you have to do that in a way that you still respect detailed balance. So in order to do that, we have so-called adds, birds, kills, merges, and splits that send the sampler state from one point in one model to another point in two different or a separate model, basically. So you can think of all these submodels as components of a much larger model, which I like to usually call the meta model. The meta model contains all these as nested subgradients. And in terms of the strong lens problem, you can think of this as the space of all lens models that you could use to fit a data, say an LSST image or an HST image, which contains as submodels lens models with different complexity, say with a certain number of subhalos, with a certain number of macro lens structure, with external shear or without external shear, etc. So you can name the amount of complexity you have. If you wanted your sampler to consider these all at the same time, there's a Jacobian that connects these, and the sampler essentially calculates it for you to take steps across all these different realizations of a lens model. Now, in this sense, you will, I think the first thing you will wonder about is how are you keeping this model well behaved? In this amount of flexibility, it's really hard to make sure that a model actually doesn't overfit. So the notion of parsimony is central to probabilistic cataloging. Here is a quick sketch, which was going to be a quick sketch, but it's not working. It's an animation, but it basically, so I'm going to draw my hands again. If you can draw a straight line through these points, and that would be a so-called underfitting situation, or you could connect all the dots, and that would be an overfitting situation. But if you actually come up with just the right number of breaks, then it's going to give you basically the set of all the lines consistent and all the breaks therein consistent with the data. That's what we are trying to do with PCAT or probabilistic cataloging. This is achieved using the Bayesian evidence, but in a transdimensional sense, because in a Bayesian evidence, typically this integral is taken over a single model. In PCAT, the integral is taken over all models within the meta model. That's the difference. And it obviously then implements the Occam's razor. So here, the model M2 is preferred, as you can see, because it can fit the data, but do so with the fewest number of parameters. And one caveat that you may or may not realize in this level is that when your parameters, say, for example, in the lensing problem, have very low mass, say you have subhalos, and they are so small mass that they don't even contribute to your lens model. You might run into situations like that. So Bayesian evidence makes sure that those subhalos are penalized, because otherwise you will have a lens model pretty much with lenses that don't do anything, and you don't want that to happen. So in order to do that, we have a regularization prior that we put on the overall prior, which is half the number of degrees of freedom, which comes from the Gaussian approximation. And when we do that, basically we can make sure that all the parameters are bounded. Okay, so applying this idea to strong lenses, basically a few years ago, I led a paper where there's the whole notion can be described by this probabilistic graphical model, PGM. So at the top, you've got basically the so-called hyperparameters. As you might remember, I told you that this is a hierarchical model. So then you have the blue, the dimensionality, which is a very key parameter. It's a discrete parameter. And then the green and the yellow ones are essentially the subhalo, masses, positions, cutoff radii, scale radii, and then you've got some parameters that model the PSF and the background, the sky background, and all the other parameters about the macro lens model, such as the eccentricity, the total mass to light ratio, etc. And eventually it forward models the image and does that within a usual PCAT scenario. So this is some simulated image, and with green you can see the subhalos, and with blue you can see the fitted subhalos. You can see that the large squares that are close to the multiple images are typically fitted for, and those that are farther away are not, because there is no information content that comes from the parsimony I was talking about. And so what comes out of this is the following. So I was going to talk about the H-naught problem, so let me first do that. So when you do PCAT, you take a lot of samples in the so-called catalog space, and at the end, what you are left with is a bunch of samples, and you really don't trust any one sample as an individual sample, but you trust its posterior distribution. The only difference with respect to traditional Bayesian inference is that these samples live in different dimensions. So you have to really marginalize to put them on a certain map, because some models will have 2, some models will have 5, some models will have 10 subhalos, say, for example. Now, the histogram here shows the mass locked up in the subhalos, and its histogram basically is the posterior distribution. So the green is the true value, and the posterior is very much consistent with that. This is essentially the measurement of substructure in the absence of very high signal-to-noise subhalos. Similarly, here, this is the mass distribution. And you can see that the blue, which is the posterior, is roughly consistent with the green, which is the true, unless you're at the very low mass end, which due to the parsimony prior starts to go down. Again, this is so that we don't fit for nothing. And this is the resulting convergence map. You can see that the ink here, which is the posterior convergence, roughly traces out the crosses that are close to the multiple images, and green circle is the Einstein radius of the macro lens here. And this is an experiment that I don't have much time for, so I'll probably use it in the questions if it comes up. So let me just start summarizing here, and then let's get some questions. So the summary of the idea is that you basically go for the unknown unknowns in your problem. So instead of taking a particular model and choosing your parameter set and fitting for it, you choose pretty much the whole space that you could think of across dimensions that are all consistent, and then apply a robust set of parsimony priors so that you can squeeze out all the information there is in the data set, and then you apply this to the strong lens problem. And this allows you to get basically a catalogs or set of samples in the catalog space of subhalos, substructure, consistent with the high resolution data. Again, in LSST, this is still relevant, but not for the very small subhalos, but rather when you treat in clusters, for example, when you treat the galaxies themselves as subhalos of a much larger cluster, the same idea applies. So I don't want to focus on the very low mass end of this subhalo mass distribution, but rather keep it as a generic idea. So with that, let me conclude and take questions.
Any question? Come on. So let's go first to Anwar.
Hi, thank you for the nice talk. So I'm wondering if PCAT is a sampler as a software, or do you also have the lens modeling part? So I'm wondering, for example, can I use PCAT as a sampler, but doing the lens modeling work, the simulation work in lens astronomy?
Yeah, so PCAT is a reversible jump Markov chain Monte Carlo sampler. As a generic software, it can even do non-astro problems. It just treats this as an abstract set of elements consistent with data drawn from a metamodel. The 2018 iteration was a likelihood function and the necessary bookkeeping, so to speak, to make this immediately useful for strong lensing. Yes. It's in Python, but parts of it are accelerated with GPU and C. So it's the likelihood evaluation is pretty fast. So the typical thing, and I don't know if this will come up in the questions, but it can be a little slow to do this. So it basically tries to overcome that weakness by having the forward model pretty optimized. So every likelihood function you write needs to be lightning fast in order for you to be able to propose many times.
Yeah, in respect to that question, how does your sampler, how do you know it's converged and it's not just in some local minimum, especially when you're talking about this large, really complex space?
Great question. Yes, so there are many metrics that I evaluate to ensure convergence. However, there's one thing I have to mention, which is that evaluation of the convergence of a meta model is different from the evaluation of a single model, because when you have a single model, you can look at the autocorrelation time of individual parameters. In meta model, you cannot do that because it's ill-defined. You just can't do that. So you have to basically come up with fixed dimensional so-called diagnostics. You reduce your multi and variable dimensional space into a set of fixed dimensional vectors, and you evaluate on that. And typically, that's your forward model. So every pixel in your output, like when you do the forward modeling, has to converge. So the stationary distribution of your predictions have to be converged, and that's a very strict requirement.
Can you mute? 2 more in person and then online.
Thanks a lot. Since you mentioned that the PCAT can be applied also to non-astral problems, could you say maybe a few words about how tuned it is specifically for strong lensing? So would it, for example, work out of the box as an RGMC-MC sampler for like a gravitational wave problem, or some other problem that is completely unrelated to strong lensing?
Right. So the out-of-the-box non-strong lensing aspect is that it allows you to input your own likelihood function and also a set of elements. And these elements are abstract. Again, just to define element very precisely, it's a subspace of your meta model that occurs and again within your meta model. So it's basically identical subset. So in your point source model, for example, you've got 2 positions, 1 flux and potentially a color or something like that. So as the user, you only provide 2 things, the likelihood function and the priors on these elements. Those are the things that are inputted into PCAT in the non-strong lensing or generic mode.
I think you kind of answered my question just right now, but just to be sure, how much choice do you have to make with regard to the dimensionality that you want to explore? For instance, how many interlopers you allow your model to explore?
Right. Oh, by the way, when you say interlopers, I don't have interlopers in my strong lens model, but yes, thanks for the note. So to really respond to that, I will bring up this PGM again. So you see the blue dot there, it's actually a model parameter, which is the dimension of the submodel that your sampler is in. So it's a discrete parameter, it's the number of elements in your model, and you actually have a prior on it, because it's a model parameter. So there's a parsimony prior that acts on the blue dot, which is like very central. So the user can choose also that part, which is very important.
Just to follow up, but the blue dot links to the green dots, which means you have to make a choice of how many of these green dots you're going to put, right?
Yes, the user does that. Yeah.
Yes, and we have one online. Alexandra, please go ahead.
Hi, thanks a lot for the nice talk. I was wondering if you could talk a bit about how you choose the transition rules between models, because I guess that you need some knowledge of like how different models are correlated with each other with different numbers of subhalos, which could be kind of complicated. And I was also curious, like how you divide up the proportion of jumps within models versus between models. So yeah, I was wondering what thoughts you could share about that. Thanks.
Yeah, thanks. Yeah, very, very good questions. So, well, first of all, there's an assumption that goes into the transdimensional moves, which is the assumption of locality. So you assume that within this sub-parameter space available to a single element, there's some locality in which, if you really take the limit, you assume a delta log likelihood of 0. So basically, a proposal will return the same likelihood in the limit of this locality. For example, for point source problem, it's really the position, because if you so-called split a given point source into 2 point sources at the same location, the likelihood won't really change, but the prior will, and it will be penalized, so you'll really not accept that proposal anyways. But in general, there's essentially a parameter or set of parameters which keep these elements so-called local. And for the merge, split, or birth, death proposal frequency or relative frequency, the user can choose these because these will be very problem dependent. For some problems, births and deaths are more important or more efficient ways of sampling from the posterior, whereas in other problems, merges and splits are more efficient. So the user can choose that.
Okay, thanks a lot.
Great. Let's thank Tansu again. And if you have further questions, Tansu is around on Slack and in person. And now it's